the serial example from the stack machine page requires a clock frequency of 50.4 megahertz to have the correct baud rate as written. If you go into the RS-232 modules, you can change the prescaler value to be any frequency you want. Let's say 50 instead of 50.4. What possible reason did I have for using 50.4? Well, it happened to be exactly twice the video control frequency, and so it was handy because it was phase locked with the video control frequency. But to get the baud rate right, to see characters on putty, you need to set the so-called fast clock to 50.4 megahertz. And that worked, yes, right? Yesterday it worked fine, yeah. So, any questions about the CPU or the compiler? How many people have run any code at all? One person. You got to start on this, folks. Time's wasting. If you leave it till this Friday, you're going to be looking at doing a two-week lab in 1 week. You won't like it. So, talked about audio codec last time. Getting the audio codec running should be fairly straightforward, but it is yet another technology you're going to have to figure out how to test. So again, get started on it. Today I want to talk a little bit about linear filters. And the goal here in filtering is to discriminate two signals, or discriminate signals based upon the history of the samples. We're going to be talking only about causal filters, which means filters that act in real time, and filters that act in real time can't know the future, right? They don't know what's going to happen next, and so they have to make, so the filters have to make decisions. They have to be able to discriminate signals based upon the history of the signals. Now, for digital signals, that means past samples, and we're going to limit ourselves to systems that are sampled at a uniform rate. So there's going to be some sample frequency, Fs, and we can look at as many samples in the past as we want to try and discriminate a signal from another signal. But every time you add more data, it increases the cost of the calculation. So there's going to be some trade-off in what we can discriminate versus how much time we can spend computing. So, so what is a filter? What kind of things do you want to discriminate? Well, if we have some log frequency versus log amplitude plot, we can say that what we want to do with a filter is perhaps discriminate two sine waves from one another. We want to know when sine wave at frequency A versus frequency B exists, and so we would like to have a filter which perhaps two filters that look like this, where this is the filter for A and this is the filter for B. And so any output in this filter channel means that this sine wave exists, and any output in the B filter channel means that the B sine wave exists. So you might guess that one aspect that we're interested in for filters is how well can you discriminate two frequencies? So one perhaps use for this will be to have a sharp filter which cuts off two sine waves that are close together. Another possible use might be to discriminate a signal. Now I'm going to draw a power spectrum. So there's a power spectrum of a signal. Let's say we have a signal with a fairly sharp set of peaks in it, and then a fairly high background of noise at high frequencies. A situation like this often happens in biology. It also happens in instrumentation. You're trying to record some acoustic signature in a car while you're driving, and all you can hear is wind noise. So in this case, what you would like to do to separate out the signal from the noise is you would like to have a filter which distorts the signal as little as possible. So the filter has to be quite flat in this region. It has to have a uniform response in the signal region. And then it has to attenuate the noise very well. But the transition speed between those, the rate of cutoff, may not be as important as it is if you're trying to discriminate two sine waves side by side. So the goal here is to build computational processes, build filters that will either discriminate frequencies well or separate noise from signal well with optimum flatness. Or another possibility is that I want to look at the time domain. I want to get rid of noise on a square wave and distort the shape of the square wave as little as possible. So I want to attenuate the noise while not changing the shape of this. I don't want the output to look like this. I want it to look as close to a square wave as possible, but just without noise on it. So there are various criteria that we want to be able to perform, and we can summarize these: that the filter should have some combination of good cutoff rate for discrimination. It should be flat in the pass band. It should be flat in the pass band to allow small distortion of signals that we desire. It should have good attenuation in the stop band. Again, looking at an example like this, we want the noise to be heavily attenuated, and it should have good pulse response. Not too much distortion in the time domain. So clearly, what you want, clearly what you would like, what you desire, is a filter whose frequency response, log F versus log A, looks like this. It's flat until it drops instantaneously, and then its output is 0. And you can never do that. Or let me put it differently. Such a filter requires infinite computation, so it's not practical to do. Why does it take infinite computation? Who'd like to hazard a guess? Joe. It is infinite in the time domain. That's right. That's a very mathematical description of it. Another way of saying that is that to cut something off sharply means that you have that you can discriminate two sine waves that are infinitesimally different in frequency, right? All right, so let's plot out two sine waves that are infinitesimally different in frequency. How do we tell those apart exactly? We have to wait a very long time until they diverge, if they're only slightly different in frequency. And so it requires a lot of time, which means it requires a lot of samples, which means it requires a lot of computation and memory. So the best we can do is some approximations. But let's write out a general form for any questions? What I'm going to ask you to do in lab 2 is a fairly simple set of filters. I'm going to ask you to produce one of 4 filters that will be switch settable, click, clickety, click, on the DE2 board. One of which is a low-pass filter, I believe with a cutoff of 500 hertz. Again, this is log F versus log amplitude. Another is a high-pass filter with a cutoff of 500 hertz. And the third one is a band-pass filter with a cutoff at 500 hertz and 2 kHz. And then I'll ask you to verify those responses by passing sine waves through it, measuring the amplitude output. I'm not going to ask for very sharp cutoffs, because we want to keep the computation fairly simple. But there will be some. What we want to talk about today is how you're going to design these. And the basis for the design is going to be referred to as a direct form to transposed formulation, which it turns out is what MATLAB uses, and so it's easy to compute with. If we have some new filter output yn, we want to compute the new filter output as a linear combination of past samples. We're actually going to put a coefficient in front of yn. MATLAB always sets this to 1, but you might not want to. Formulation in MATLAB is you have some b1 times x of n. So this is the newest output. This is the newest input. This is the current time input, multiplied by some constant, plus b2 times x of n minus 1. That's the input before the current one. And we're going to do some number of samples up to b of nb plus 1 times x of time n minus nb and that's all the information we have about the input. We can use as many samples as we want, but in the end we have to have a finite sum, and if we want the system to be linear, we have to use a linear constant coefficient filter. We have to use constant coefficients multiplied by each input value. Then we're going to subtract off previous outputs. So now this is the last output of the filter before the current one. A3 times y times n minus 2 minus dot 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 a n a plus 1 times y of n minus n a. So that's all there is. You're going to form a big sum. Yeah, if you want to think in those terms. So you can write any set of B's and A's, any set, and build a filter. It turns out there are person-centuries of analysis in finding the best set of B's and A's for a given kind of filter with a given sharpness and cutoff rate and phase shift and pulse response and so on. But they fall into two basic types, so-called finite impulse response and infinite impulse response filters. For a finite impulse response filter, all of the A's equal 0. A1 to ANA equals 0. So it's for a finite impulse response filter, only inputs are used and no outputs from the filters. As soon as you include one output, then you have an infinite impulse response filter, meaning that the output in some sense decays exponentially for a very long time. So let's do a couple of examples. Well, the first filter that everybody thinks of when they want to build a simple low-pass filter is a so-called running average filter. And this is a very simple running average filter times xn plus 1/3 xn minus 1 plus 1/3 xn minus 2. That's a perfectly good filter. It averages together 3 samples in a row. So you'd guess it is a low-pass filter because fast changes are going to be smeared. Right? But it's a lousy low-pass filter. But it's used everywhere. Doesn't mean it's good. It just means it's used everywhere. In general, finite impulse response filters, now I'm not going to prove this, I'm just going to state it. We can talk about it more if you want. In general, finite impulse response filters give you more controllable phase shift. They give you there are a set of design tools which are completely arbitrary and allow you to have any shape filter that you want. So-called, Parks-McClellan algorithm. Infinite impulse response filters act more like their analog equivalents, and so there's a certain number of engineers of my age who feel more familiar and comfortable with infinite impulse response filters because they're like the filters we used to build with op amps. But a more basic reason for liking infinite impulse response filters is you get about 10 times the bang for the buck. You can make a filter of a given sharpness, with about 1/10 the operations if you use an infinite impulse response filter compared to a finite impulse response filter. And so if you are computation limited, if you don't have some big kick-butt 3 gigahertz machine, but you're trying to use a microcontroller, say, then it makes much more sense to use an infinite impulse response filter and to suffer the increased design difficulty, the more uncontrolled phase shift in return for a sharper cutoff function with less computation. Any questions? Such a quiet group. So, what's an example of an infinite impulse response filter? Well, let's first of all do the analog version of a simplest possible low-pass filter. And convert that to a digital filter. So let's see. If we have V out there, then tau dV out. Let's just call this V because I don't want to write out every time. So we have that tau dV dt plus some constant times V is equal to V in from Kirchhoff's laws. And we can rearrange this, and then we have to use some scheme to convert it from a differential equation to a difference equation to quantify it, to get it into this form. All right, so we want to convert it from a differential equation into this form. So we can write this as tau V of n minus V of n minus 1 over delta t, where delta t is equal to 1 over the sample frequency. Equal to minus k times V of n minus 1 plus V in of time n. Then we can just solve this out for Vn. This is an explicit form. So we can solve this out for Vn. And we'll find that we have a form. Wow, this already looks pretty much like that. We have tau over delta t times v vn equals tau times delta t over minus k times v n minus 1 plus v n of n. So that says then that we can identify this term, tau over delta t, as A1. Actually, minus, yeah, A1. And we can identify this as the unity here is B1. And we can identify this as Vn minus 1 would be minus A2. So we've just taken some differential equation, discretized it, and when we discretize it, we come out with a form that looks like this. So this is really, depending on how you like to look at things. I like to look at things as differential equations. That's just the way my brain works. And so I like to think of the filter equation as a discretized differential equation, but you don't have to think of it this way. You can think of it as an abstract algebraic manipulation of past samples that gives you some optimal filter. Any questions? So what we're going to ask you to do for Lab 2 is I'm going to ask you to implement this equation on the CPUs that I wrote. I'm going to ask you to implement this at a rate that's high enough. It has to do the calculation fast enough to be full audio rate. In other words, you have to calculate a new sample output every 22 microseconds. That's not hard on the FPGA. That's easy. You have to calculate a new sample every 22 microseconds for each channel, and I'm going to ask you to do the two filter operations for the two channels separately. Separate CPUs. So the software you write is going to be a straightforward piece of numerical analysis that does a bunch of adds and multiplies, adds them together, and spits them back out of the audio codec. So each new input is going to come from the audio codec as a 2's complement 16-bit number. You're going to have to keep track of a history of some number of inputs in local memory, in your computer memory, and locally keep track of outputs, again, in your computer memory, and emit this sample back out to the audio codec to be listened to. I don't think it's a lot of code. Probably not more than 100 lines of code. Probably less than that. The interesting part of this is the interfacing to the audio codec and the synchronization of the calculation with the audio codec. because you don't want the CPUs to run at full speed calculating as fast as they can, because you'll find that the CPUs run a good deal faster than is necessary for this application. You only want to do one calculation per sample. Any questions? This is a really quiet group. People, you need to start asking questions. So I'm going to talk a little bit more about filtering, but I'm not going to talk any more about programming this up in a serial sense, because I think you can all do this. I want to talk more about filtering on the FPGA hardware. You're not going to do this for this lab, but you might want to do it later in the semester. If you want to build a very high-speed filter, let's say you want to build a software radio. Software radios are all the rage these days. Make a good final project. If you wanted to build a software radio that ran at 10 megahertz, then you would not be able to implement this equation in software running on a CPU, but rather you would implement it in parallel, running on multipliers and adders instantiated in hardware. I do want to talk a little bit about that. One of the interesting aspects of this calculation, though, in serial hardware, which is what you're going to build, is that you have to worry quite a lot about round-off error. Sometimes these coefficients get small. If you ask for a filter that has a narrow bandwidth, then at least one of the coefficients is going to get very small. And when that happens, you're going to find that with a fixed point calculation, you're going to run out of bits. And then you'll instead of getting a small answer, you'll get a 0. Something won't cancel correctly. You'll get a 0 where you should get some cancellation. And the filter won't operate properly. So you're going to have to worry quite a lot in this lab about finite bit approximations, finite word length approximations of digital filters. So when you design your filters, and by the way, I would say the best way to do that is to use MATLAB. I'm going to ask you to build Butterworth filters. Butterworth are optimally flat in the sense that the slope of the amplitude function has all 0 derivatives at f equals 0. Okay, so it's optimally flat in that sense. I'm going to ask you to use a Butterworth filter. The MATLAB command for designing Butterworth filters is butter. You give the number of poles that you want. Let's say 2. You give the cutoff frequency in units of 1/2 the Nyquist in units of the Nyquist frequency. So this is in f over fs over 2. This command with the parameter b comma a here will generate the b vector and the a vector for you. If you do this for a small f, you will find that these coefficients get quite small, that b and a become quite small. This will build a low-pass filter This will build a high-pass filter. And see, the noise is terrible here. This will build a band pass filter. If you evaluate, let's say that you're using 10-8 format. Let's say you don't rework the multiplier, but just use the multiplier I gave you. If you use 10-8 format and you find that one element of B or A gets down to 0.003938, that will now evaluate to exactly 0 in fixed point format. That's not a good thing. So any coefficient smaller than about 0.004 in 10-8 format will evaluate to 0, will not behave properly. And so you either have to extend the number of bits or you have to modify your filter design. You're going to lose points if the filter doesn't behave the way it's supposed to. Let's say that we asked for an optimally flat design like this, and what you got was something that looked like that. That will cost you. Therefore, you need to pay attention to round-off error. Come back with questions on Friday.